Good evening, everybody. My name is Rose. I'm with the Academy of Science St. Louis, and we are one of the sponsors of tonight's talk, along with the St. Louis Zoo, and we're very pleased to be partnering with the zoo to bring you tonight's science seminar. Before we get started this evening, I'd like to tell you a little bit about the Academy of Science and who we are. We're an independent science organization. We're supported entirely through community contributions, and we've been around for a very long time, since 1856. It's our mission to promote the public understanding of science and inspire the next generation. And at venues throughout the region, we do that by connecting science and the community through free and or very low-cost public talks, science seminars and workshops, and trips and tours that celebrate science at venues throughout the metropolitan St. Louis region and surrounding counties. These trips, tours, and talks feature scientists and engineering professionals of both national and international renown. In addition to advancing the public understanding of science, as I had said, it's our mission as well to inspire the next generation. We do that through a number of free and low-cost opportunities that are expressly for teens, such as our Teen Science Cafes, Teen Cafes Youth Leadership Council, and Junior Academy of Science. The Junior Academy is a pre-professional STEM membership organization for students in grades 6 through 12 that offers hands-on opportunities in science, engineering, and medicine. Teens can attend unique behind-the-scenes explorations of leading engineering, technology, and science labs of our region. They can access university libraries, participate in field opportunities, and challenging and engaging science competitions for a full range of academic levels. And Junior Academy members make real-world connections, meeting top STEM professionals. So if you know a student or students, or you are a student in grades 6 through 12 with a love for science, memberships in the Junior Academy make great holiday gifts. You can find more information on the Academy and all of our community-wide events by visiting our website at academyofsciencestl.org. You may also visit us on Facebook or Twitter, or before you leave tonight, pick up some of the literature that is on the table just outside the auditorium. I do want to mention a couple upcoming Academy events you might have an interest in attending. On Tuesday evening, December 9, at the Missouri History Museum, retired University of Missouri-Columbia Associate Professor of Fisheries and Wildlife Sciences and the Nature Conservancy's Great Rivers Partnership Science Advisor, Dr. David Galat, talks about an ecological history of the Missouri River and 21st century challenges in the Big Muddy. This event is free and open to the public. You do not need to register to attend. And then on January 28, on the Washington University Medical School campus, and as part of our Teen Science Cafe series, radiology and biomedical engineering professor, Dr. Susan Lappe, talks about nanotechnology and the science of the small. Teen Science Cafes are open to all students in grades 6 through 12. They are interactive, they are free, and there is food. But you do need to register to attend, and you can do so by logging onto our website, again, at academyofsciencestl.org. You can find even more science opportunities, talks, and tours on our website or listed on the event flyers and Academy literature that is available for you to take with you before you leave this evening. If you'd like to receive e-notification of upcoming Academy public lectures and events, there are some e-news sign-up sheets that will make their way around the audience. If you are a student and you need to verify your attendance at tonight's talk, there will be some verification cards that are available following tonight's Q&A, also out at the table outside the auditorium. Please turn off cell phone ringers or any other electronic devices that might make noise during the program. With all that said, I'd like to introduce this evening's speaker, Dr. Lihong Wang. Dr. Wang earned his BS and MS in optics from Zhejiang University of Science and Technology in Wuhan, China, and his Ph.D. in electrical engineering from Rice University. He is a fellow of the Academy of Science St. Louis and a recipient of the Academy's 2014 James B. Eads Outstanding St. Louis Scientist Award, recognized for his seminal work in photoacoustic tomography and biophotonics. He is currently the Jean K. Beare Distinguished Professor of Biomedical Engineering at Washington University in St. Louis, and his book, Biomedical Optics, Principles in Imaging, was one of the first textbooks in the field, garnering the 2010 Joseph W. Goodman Book Writing Award. Dr. Wang is also the co-author of a book on polarization and editor of the first book on photoacoustic tomography. His laboratory invented or discovered, get ready, functional photoacoustic tomography, 3D photoacoustic microscopy, the photoacoustic Doppler effect, photoacoustic reporter gene imaging, focus scanning microwave-induced thermoacoustic tomography, universal photoacoustic reconstruction algorithm, frequency-swept ultrasound-modulated optical tomography, time-reversed ultrasonically end-decoded optical focusing, sonoluminescence tomography, Miller matrix OCT, optical coherence computed tomography, and oblique incidence reflectometry. His Monte Carlo model of photon transport in scattering media is used worldwide. He has published over 380 peer-reviewed articles and delivered 382 keynote plenary or invited talks. He is prolific and well-known across the globe, and we are very pleased to have him here with us tonight. He's here with us to talk about photoacoustics and other optical engineering breakthroughs in biomedical engineering. On behalf of the Academy of Science St. Louis and the St. Louis Zoo, won't you please join me in welcoming Dr. Lihong Wang.
Well, thank you, Rose, for the very kind introduction. Thank you all for coming here tonight. I'll be talking about several technologies we've been working on in our lab. Our goal is to image biological tissue using optical contrast. Starting from the motivations and challenges in our field in general, I'll be talking about two major incarnations of photoacoustic tomography, namely photoacoustic computed tomography and photoacoustic microscopy. Then I'll talk about some of the newer technologies we've been working on, time reversal and compressed ultrafast photography. The very first question is, why do we bother with light for imaging purposes? You know, when you walk to a hospital, you go to a radiology department, you'll see a lot of imaging modalities already, MRI, ultrasound, X-ray, why not? Now, first of all, it's very safe to use light because we're receiving light or optical photons all the time, every day. So we're dealing with what's called non-ionizing radiation, right? The radiation involves photons of very tiny energy. You're talking about electron volts as a unit for photon energy. So when you're talking about a couple of EVs, then the photons are not energetic enough to ionize molecules. Very safe. But when you use X-ray photons, they're so energetic, thousands of EVs. They'll knock off electrons out of molecules, they'll ionize tissue and cause problems such as DNA damage. And so the ionizing radiation part of the EM or electromagnetic spectrum causes problems, right? So we're working in this region, which is very safe. More importantly, from a very fundamental perspective, which is the physics, that tells us light occupies a very special region of the EM spectrum. This is the only part of the EM spectrum that allows us to probe molecules directly. So we have access to the molecular information. We know the importance of molecules in biomedicine, right? So we have to use light. And because light can probe molecules, we can apply this to biomolecules, all the biomolecules you can think of, right? You can read the 4 major classes of biomolecules, right? Some other endogenous or intrinsic biomolecules, right? Or even exogenous molecules. You know, later on, I'm going to make a point that, in fact, by using photoacoustic tomography, we can potentially image any molecules, right? So this can be extremely powerful. By imaging biomolecules, we can provide all sorts of imaging functionalities. For example, in vivo functional imaging, very much like functional MRI you might have heard of. So X-ray will image structure very well, but X-ray may not be able to tell if a piece of tissue is alive or dead, right? So we want to image not just the structure of the tissue, but also the physiological function. And photoacoustics or optical imaging in general can provide that type of information. in vivo metabolic imaging. So this is somewhat like PET imaging, positron emission tomography. We're looking at metabolic parameters, right? So I enumerated a couple of examples, such as the metabolic rate of oxygen and glucose consumption rate. We all know that these are the two major mechanisms of metabolism in our body, right? In vivo molecular imaging. So we're able to image all sorts of biomarkers which can potentially be hallmarks of cancer, for example, right? And we can image reporter genes that allows us to track gene expressions. We can even provide label-free in vivo histological imaging. As we know, standard histology is invasive. When you go to a hospital, if the physician said, we need to do a histology on you, that means they have to excise tissue out of you, right? So that's invasive. Then they'll go through a series of procedures and prepare the tissue before they can examine the tissue slices under a microscope. So the whole procedure is ex vivo, invasive, and takes time. Can we move this technology and transform this to an in vivo situation where we can look at a tumor margin, right? As we know that a lot of cancer patients die because the cancer cannot be removed 100%. So there's small residual of cancer cells that are left around, right? So then the cancer will grow back. Can we use our technology to demarcate and basically find the boundaries of the tumor and remove the cancer 100%? So that's going to save lives. There are many, many reasons why optics is so powerful, but we face challenges. One of the challenges is called diffraction, right? In high school or middle school, we were taught that you can focus a light beam through a lens to a geometric point, right? If you say that in high school, you get a full mark, right? But if you say that in college, the professor may tell you you're wrong, right? So because light is a wave, any waves cannot be focused to a point, a geometric point, right? The ultimate size of the focal point depends on the wavelength, right? In this graph, if you do your best, try to focus as sharply as possible, make this angle alpha 90 degrees, your focal size will become wavelength over 2, right? That's how small you can focus. This is called the diffraction limit. So waves will diffract. This year, 3 of our colleagues working in our field were awarded the Nobel Prize in chemistry, actually, for breaking through this limit. So this limit has been overcome. They can generate resolution smaller than the wavelength, right, which is amazing achievement. Now we face even more challenges in penetration, right? Our intuition tells us light will not penetrate through tissue because we can't even see through our own palm, right? So when we close our eyes, our eyelids is going to block all the light. We can't even see the outside. But you will actually see light, right? This is why some people, when they sleep, they have to wear blindfolds. You have to wear blindfolds. Our eyelids are not dark enough. They're not blocking enough light, right? So photons, basically it's a quantum term for light. Photons will actually go through the eyelids and reach the retina. And this is why even when you close your eyes, you will see some light. Where's the challenge? If we want to penetrate tissue and get images, 350 years ago, microscopy was invented, right? That really revolutionized medicine, right? Before that point, there was no technology that allows us to see cells. With wide-field optical microscopy, we can see cells now at micron resolution. However, you have to cut the tissue into very thin slices, like 10 microns in thickness. And this is still the standard technique for histology or standard pathology analysis. So what I call the penetration limit in this case is the aberration. right? So the wavefront distortion, in order to form a very good image, you have to have a very regular wavefront. You have to have a controlled wavefront. So in tissue, because of the distribution of refractive index, in other words, the speed of light will travel, light will travel at different speeds of light, depending on which part of the tissue the light is traveling through, and that gives you a problem. That's going to cause distortion and preventing us from forming a good image. Right? So that problem was overcome about maybe 20 years ago using modern optical microscopy. You might have heard of confocal microscopy, two-photon microscopy, or even optical coherence tomography. Right? These are really modern wonders of optical imaging technologies. Those technologies will reject multiply scattered photons. They'll retain the unscattered or singly backscattered photons for imaging. And they will sharpen up the images. They overcome this aberration limit and penetrate from the original limit of, say, 100 microns to about 1 millimeter. By the way, 100 microns is roughly the diameter of our hair. That's how small it is. 1 millimeter you can picture. If you have a little ruler, you can picture 1 millimeter, right? So 1 millimeter doesn't sound very big, but it's a huge advancement from 0.1 millimeters. So 100 microns is 1/10 of a millimeter. So that's a factor of 10 enhancement in terms of penetration, right? Those technologies have impacted biomedicine enormously, right? Not just for biology, but they've also been used in medicine. If you go to your ophthalmologist one day, they may actually use OCT, optical coherence tomography, to examine the retina for you, right? Because without OCT, you can only see the surface of the retina. You can't go beyond the retina. There might be something going wrong. Sometimes it's behind the surface of the retina. OCT is able to see through the entire retinal layer. Very, very powerful technique. However, this set of modern optical microscopy techniques face the next challenge, something I call diffusion limit. Right? So they cannot go beyond 1 millimeter in depth in biological tissue. How do we overcome that problem? So we use photoacoustic microscopy, or in general, photoacoustic tomography, to overcome this problem, right? Where we actually use multiply scattered photons. So I have a little cartoon here. Conventional microscopy uses straight propagating photons. The modern optical microscopy will tolerate a little bit of scattering because they can reject multiply scattered light. But to go deeper, we have only multiply scattered light left. So you cannot afford to reject multiply scattered light. Otherwise, you will get no signal. So we have to use those tortuous paths for our light propagation, and somehow we have to get spatial information, right? So that's the huge challenge, because oftentimes when photons wander around through this tortuous path, you lose spatial information. So that means you're not going to get a sharp image. We somehow have to form a sharp image. Our solution is to use photoacoustics. And as a result, we advance the penetration not just by 1 order of magnitude, by more than 1 order of magnitude, almost 2 orders of magnitude. Now we're able to penetrate multiple millimeters, even multiple centimeters. So you're talking about not only skin level penetration, but also organ level penetration. I'll show you some more examples later. Like anything else, we face the next challenge, right? We cannot penetrate beyond right now 7 centimeters. How do we target the next challenge? This limit is called the dissipation limit, because beyond this depth, even the multiply scattered photons are spread around, so they're not very intense, even though you have a lot of photons at that kind of depth. So the next natural question is, can we gather those photons and make them intense? Right? So there's an upcoming technique called wavefront engineering with the internal guide stars. There's hope there. There's hope that we can potentially break through this dissipation limit and reach the next level. This could be extremely exciting if we reach there, because Now we're talking about tens of centimeters of penetration by using safe light. Now we're talking about potentially whole body human imaging using non-laser radiation with rich contrast information. So very, very exciting. I'll touch upon this topic later on. And this is related to time reversal. Right. Now, of course, the ultimate limit is the absorption limit. If you take all the scattering centers away out of the body, all you have left is absorption. Right? So that's going to limit your light penetration. Likely, if you use the right light wavelength, the right light color, that penetration is extremely long. It's like a meter or so, right? All right, so let's take a step back and ask ourselves the question, what does it take to get a good image? Right? We all know how chest X-ray works, right? Chest X-ray works so well because X-ray does not scatter so much in tissue. Right? You get what's called ballistic light, ballistic photons in the X-ray regime. Right? So that's going to cast a shadow directly for you, and you can see the bones and certain structures. If you mimic X-ray projection by using light, when you have certain tissue thickness, you're not going to see a shadow at all, right? Because light will follow a highly tortuous photon path before reaching your observer, right? So on this side, you won't see a shadow. If we surgically cut open the tissue, right, that's invasive, of course. Now, the right-hand side is very well defined because this is all exposed to air, and the photon path will be well defined, allowing us to form a very good image, despite the tortuous photon path on the left side. So the point I want to make is you only need one-sided clarity. You don't need both illumination clarity and detection clarity. Well, this is so invasive, it's not very useful, right? A better idea is called optical clearing. So we can introduce certain chemicals into the tissue that's going to turn the tissue transparent, right? So that's going to achieve the equivalent to K-speed, giving us a very sharp image. Unfortunately, this process is toxic. So you may have turned the tissue transparent, but this is going to kill the tissue. So it's not very useful for in vivo imaging. What we are doing is to convert light or photons into ultrasound signals. So we're talking about acoustic signals here through the photoacoustic effect. Acoustic scattering is orders of magnitude, like 1,000 times weaker than optical scattering. Equivalently, on the detection side, we've reached K-speed or Kc without invasiveness or toxicity. So on the detection side, now we're dealing with transparency that allows us to form a sharp image. So that's the basic idea behind this technology. Right, let's see. I'll give you more demonstrations later on to make sure we understand the concept. Photoacoustic, very much like X-ray CT, there's also photoacoustic CT. We have different geometries. I'm going to talk about circular geometry first. Photoacoustics as a physical phenomenon has been around for over 100 years. In fact, Alexander Graham Bell first reported photoacoustics. He actually invented the concept of photophone, right? Very interestingly, this paper was published only a few years after the first telephone was built. He had this idea of building a photophone using light to communicate. So his idea was to encode the voice or music into a light beam, then propagate the light beam in space, convert light back into sound again. You can actually hear that. So he had no access to laser at the time. That he was way ahead of his time, because laser was invented in the 50s, right? So he had to use sunlight to demonstrate this principle. Now, this idea never quite took off, right? For reasons you can imagine, because to get this to work, you have to have a line of sight communication, right? But nowadays, we have laser. This idea may actually take off again. Someone may actually revive this idea later for secure communication. We have the opposite problem than 100 years ago, right? So telephone allows you to talk between neighborhoods, without worrying about line of sight transmission. But now we're worrying about security. So between towers, for example, you have directed communication. You don't have to worry about losing your message, right, for security purposes. So of course, in Bell's days, there was no concept of tomography, right? That was not even in the lexicon. It's a totally new modern concept. We're using this very old physics with a very new modern imaging concept to form a new imaging modality. A very simple analogy I can think of for photoacoustic CT is how can we pinpoint a single sound source, single point sound source, like a thunderbolt, right? So when we see the lightning, we can reset our stopwatch. That would be our time 0. When we hear the thunder, we can record a time delay t1, multiply the time delay by the speed of sound. We would define a radius for a spherical shell on which lightning took place. If we have 3 such measurements centered at different locations, we will have 3 spherical shells. The intersection of the 3 shells would pinpoint the thunderbolt, right? So photoacoustic CT, in essence, is as straightforward as this. It's triangulation, right? Something we learned in middle school or high school, right? You can triangulate geometrically. You can figure out the source, right? Except in a real situation, we don't have a point source. We're going to use light to generate a volumetric 3D complex source. We don't know the exact source distribution because the source distribution is the image we're after. So we have to use more than 3 detectors. But this gives you the basic concept at the simplest level. So for photoacoustic CT, the first thing we do is to expand the laser beam. Very different from a common use of laser where you want to use a very high intensity to drill a piece of metal, for example. So when we talk about laser, you say, well, that would be dangerous. This is a laser beam. Here, I want to have high collimation. This is not very high power, right? So the first thing we have to guarantee is safety. What we do is to broaden the laser beam, make sure the light intensity is within the safety limit. So there's this institute called ANSI that regulates the safety of laser use. If you stay within the safety limit, you're very, very safe. Light will be scattered around, right? So if you want to image deep, you have to tolerate light scattering. We actually allow photons to scatter so you can penetrate multiple millimeters, even multiple centimeters in biological tissue. When light is absorbed, it generates some heating. We use very short laser pulses, nanosecond, right? 1 nanosecond is a 1 billionth of a second, right? Very, very short laser pulses. So this heating is very, very rapid. And we don't need a lot of heating, millidegrees, right? So 1/1000th of a degree would be adequate. That will give you a detectable signal already. So if you generate hundreds of millidegrees, then you have a very good signal to work with. That allows you to form a bright image. So this transient heating allows us to generate ultrasonic emission. It's going to generate acoustic wave through the photoacoustic effect. Right? So this is the Bell's effect. And because of the acoustic transparency, we can detect all the acoustic signals and form a very sharp image outside. However, the contrast comes from optical absorption. So we're combining optical contrast with ultrasonic resolution. Because one common question is, why don't we use ultrasound tomography? Why do you have to use photoacoustics? So in ultrasound tomography, as you know, you actually fire an ultrasound pulse into tissue, then listen to the echoes, right? So medical ultrasound imaging originated from sonar. right? So after the Second World War, scientists and physicians started to borrow that technique and applying that for human imaging, right? So what ultrasound imaging does not provide is the optical contrast. We want to have the optical mechanism as the contrast, so we have access to molecular level information. For example, using light, later on I'm going to show you, we can see the color differences of the two forms of blood, oxygenated blood and deoxygenated blood, red versus blue. Our veins, look blue, right? But arteries will look red. So ultrasound will not be able to tell the difference. And that's just one example. This is the first set of functional photoacoustic images. It's also the first set of in vivo images acquired using Photoacoustic Ct. This was reported in 2003 by our lab. And we can see actually brain activation. If you wiggle one side of the whiskers of a small animal, and the contralateral side of the brain would be hemodynamically activated. So the blood flow will change, and we can detect that change to show the brain activation on one side. And those images were acquired non-invasively. So this work really started the growth of our field. If you look at after 2003, our field really doubled roughly every 3 years in size. After 2010, the conference on this topic became the largest in Photonics West, which is a 20,000 attendee gathering, right? So this has surpassed a lot of the competing technologies or peer technologies. A natural question is, why is this technology so exciting? Well, this is probably the only technology that allows us to image from organelles all the way to organs in vivo, and we use the same contrast, right? So we use optic absorption as the contrast mechanism. So I'm plotting different implementations of this technology, right? We actually have far more than I can plot here. But this says this is a highly scalable technology. We can image at very much microscopic level, but we can also scale to the macroscopic level. This type of multi-scale imaging can be very, very important because in current medical practice or biomedical practice, for cells and below, we use optical microscopy, so we're acquiring optical contrast. But for tissues and above, we switch to non-optics. We're going to use MRI, ultrasound, X-ray, CT, what have you. So we're talking about two different contrast mechanisms, preventing us from correlating images across all the length scales. As we know, to understand a biological problem, we have to have a multi-scale understanding. You have to correlate information across the length scales. So photoacoustic tomography can potentially allow us to do so by enabling multi-scale biological research and enabling translation of microscopic discovery to macroscopic clinical practice, at least accelerate the pace of such translation. So for the 2003 work, we actually used a single element transducer that took like 20 minutes to get a 2D image. Now we have ultrasound arrays with 512 elements. Within 2 seconds, we can get a 2D image. In fact, now in our lab, we're building a system that allows us to get an image within 1 millisecond. So the technology is really getting faster and faster in terms of data acquisition. So we can image the whole body of a small animal, right, without injecting any contrast agents. We can see the internal organs, we can identify the boundaries, detect tumors, detect functions. The pharmas are very interested in this type of technology because what is the alternative to see this type of contrast? They have to use X-ray CT. The radiation dose is a big problem. To monitor the same animal for development of a new drug, you have to monitor the animal multiple time points over a time course of a couple months at least. So the radiation dose can kill the animal. And it doesn't give you enough information as well because X-ray sometimes does not provide enough information. right? You have to have the functional information to make your, to test the efficacy of the drug. Photoacoustic tomography is simultaneously analogous to MRI and PET. So this is one example. On this side, we can see the hemodynamic contrast. Right? So this is the concentration of hemoglobin. We detect the brain, again, in response to electric stimulation of the pulse of the animal on one side. You can see the contralateral side of the brain activate. So on this side, we're showing why this is analogous to PET imaging. So we're using a glucose analog that mimics glucose. So when there's glucose uptake, you can see stronger signals. Right? This is very much like PET imaging. Right? So this can be potentially very powerful in the future as well, because photoacoustics can serve as a backbone to connect with other standard modalities, like MRI and PET. We're trying to push brain imaging to the ultimate level, human brain imaging. This is an extremely challenging problem because human skull is a lot thicker than animal skull. So that causes problems because the skull has a different speed of sound than soft tissue. So this is like a photograph of an X-ray CT image of an ex vivo adult skull. And this is a photograph. And we put this canine brain inside this skull. We try to image it using photoacoustic tomography. Actually, some of the colleagues predicted this would not be possible because the skull is so thick. We got very, very encouraging data. So we got an image that shows certain structures which match the structures in the photograph very well. The next big step is to push this to in vivo imaging of human brain. Unlike X-ray CT, which always works in transmission mode because X-ray doesn't scatter much, photoacoustic waves propagate essentially in all directions. So that means we're very flexible in terms of the actual implementation. I just talked about the circular geometry for detection, but we can also do it using a linear geometry. So this is a handheld ultrasound probe that you might have seen in the hospital. We have like hundreds of ultrasound detectors along this probe. We use optical fiber bundles to deliver light. With a single laser shot, we can illuminate the volume below this linear probe. It allows us to form a two-dimensional image. So all the data will be acquired within, say, 100 microseconds. So you avoid motion artifacts when you acquire this type of images. And you can see this is actually a standard ultrasound machine. We worked in collaboration with Philips to modify this clinical ultrasound system for concurrent photoacoustic imaging. You'll get dual contrasts, photoacoustic contrast, and ultrasonic contrast. So this system works around this point, allows you to penetrate multiple centimeters and get hundreds of microns resolution. This is one example where we can see a tiny absorber buried at a depth of 5 centimeters. Right? This was not possible using standard optical imaging, right, at this type of resolution. In fact, this is a form of reporter gene imaging or a form of molecular imaging. Again, 3 colleagues received the Nobel Prize in 2008 for their discovery of fluorescent proteins you might have heard of. This is a huge discovery that allows us to follow gene expressions, but it's all fluorescence-based. But using standard optical imaging, you cannot penetrate deep. So all of the applications are limited to cells or animals at a very shallow depth. Now we're talking about multiple centimeters of penetration for this type of imaging. So this is going to extend the capability of fluorescent proteins and some of the derivatives. This technology is being tested at Washington University for human studies, for human applications. And this is one example where a breast tumor was imaged using standard ultrasound imaging and photoacoustic imaging. We can see the same tumor using a very safe light dose. The laser intensity is 1/2 of the safety limit, and the safety limit is less than 1/10 of the damage threshold. So this is an extremely safe level of light dose. We're also targeting something that might have a more immediate application, which is breast cancer staging. You might have heard that the standard breast cancer staging is invasive. You have to surgically remove the first draining node or the sentinel lymph node. What we want to do is to inject organic dye near the tumor. It's going to flow toward the sentinel lymph node. Then we use the photoacoustics to detect the sentinel lymph node and use a needle, which is guided by the photoacoustic technology, to take cells out of the sentinel lymph node to test if there's any presence of cancer cells. So once this is proven, we can convert the surgical procedure into a needle biopsy procedure. Right, this is some of the initial test results in humans. You can see the sentinel lymph node. We can see the needle here as well. Another clinical problem is to monitor the brain oxygen consumption in the surgery. You want to do it in the OR, but there's no non-invasive technique that allows us to do that well. So the current technique is invasive. You have to insert into the carotid artery and jugular vein some sensors to detect the oxygen content. So can we do this non-invasively? We can use photoacoustic tomography to quantify the oxygen saturation. We use SO2 to represent the oxygen saturation level at both the carotid artery and the jugular vein. And you'll see that they have different values. The difference in SO2 tells you how much oxygen has been extracted by the brain. So this is an indicator that tells you how well our brain is consuming oxygen. Right? If this difference is too small, that means the patient is not consuming enough oxygen. Right? You got to do something about it. Otherwise, the patient might wake up from the surgery brain dead. So we've tested 7 healthy volunteers. The average SO2 is very similar to the expected range. So this is very good news for us as an initial test. The next natural step is to move this into the OR to work on real patients. Let me move on to the microscopy domain. Unlike the photoacoustic CT, where we have to use math to form an image, you have hundreds of sensors, acoustic sensors. You get all the signals, and then you send the data to a computer, use your algorithm to form an image. Somewhat like X-ray CT image reconstruction, but it's actually more sophisticated because it deals with extra dimension. Right? So here, we're going to use acoustic lens, very much like lenses. Like I'm wearing a pair of lenses, and everybody has a pair of lenses, even if you don't wear glasses, right? Our eyeballs actually have lenses inside as well. These are biologically made. So here we're going to use the acoustic version of lenses to form an image directly. Let's just assume there's a target, a piece of tissue we want to image. We fire a light pulse to illuminate the tissue to generate photoacoustic waves. And then we use this focused ultrasound transducer to receive the signals. And you're going to get a time trace like this. So this is your time axis. You get voltage like this. You'll see a spike corresponding to where the target is. So if this guide is deeper, then this spike is going to appear later. If you have multiple absorbers or targets, you'll see multiple spikes. Because we know the speed of sound in tissue, we can convert this time of arrival into depth. So this time trace is essentially a one-dimensional image. We call that A scan, right, or 1D image. If we scan the system across the tissue, we get a 2D image. We call that B scan. Right? Now, if you raster scan on the tissue surface, you get a 3D image. Right? So that's the basic concept. And this is the detail. maybe I should skip. This photograph shows the first 3D photoacoustic microscope, which we published in 2005. So this is used to implement the idea I just described, right? So we focus light into tissue, right, to penetrate deep beyond like a millimeter, which is the limit how well you can focus, right? Beyond a millimeter, you can't really focus so well. And so we use this, what's called a dark field. We use a donut beam on the surface to minimize the surface interference, right? And then the ultrasound transducer is confocally located. You just want to maximize your signal strength, right? And with a single laser shot, you get a 1D image in the depth direction. So this head is raster scanned, XY scanned in this water tray to get a 3D image. So this system operates around this point. It penetrates 3 millimeters. We can scale to a few more millimeters if we want at expensive resolution, right? But you can get tens of microns resolution. So the resolution is getting better. This is an image of our own skin in this area of the palm. You can see blood vessels without injecting any contrast agents. If you want to get the same type of images using X-ray, you have to inject iodine-based contrast or some other heavy metal-based contrast. Even then, you will miss some of the smaller vessels because X-ray does not give you enough contrast for vessel imaging. So we all know the importance of blood vessels. Right, this is a depth resolved or B-scan image showing you some of the standard skin structures. Now we're working with our dermatology department to apply this technology for melanoma imaging. We've also miniaturized the probe, so we can use this technology in the GI tract, right? So you have to make the device tiny in order to be inserted into the standard endoscope. Somehow this movie is, let me go back and see if it'll run next time. Now it's working. So unlike standard endoscopy, like colonoscopy, for example, which only detects the surface of the lumen or the colon, right? So here we want to image beyond the surface because standard colonoscopy or upper GI endoscopy will miss anything beyond the surface. We want to see deeper, right? 7 millimeters is sufficiently deep in terms of the GI wall, right? So that allows us to see the deeper structures by providing both photoacoustic and ultrasonic contrast mechanisms. So this technology has been licensed to a large company for human translational commercialization. I'll skip some of the details on the engineering side. And this is, by the way, this is the first photoacoustic endoscope. We can also implement the photoacoustic microscopy at even finer resolution. So if we sacrifice the penetration, now we're back within 1 millimeter penetration, because we do want to cover the very top layer of the thickness. So you can focus light more tightly. That allows you to get finer resolution. And you do have to somehow collect the ultrasound wave. So we have to engineer this beam combiner, what we call light sound combiner, that allows us to combine the light optical axis and acoustic axis, make them coaxial, right? So with a single laser shot, you get a image, 1D image, and then you can raster scan to get a 3D image. So this technology works around this point, right? So your penetration is about 1.2 millimeters, but you're getting a single-digit micron resolution. So this is one example where you can monitor the same animal over time. So this is angiogenesis, meaning new growth of blood vessels, right? So we can monitor this process because angiogenesis is a hallmark of cancer. Cancer cannot grow without growing more blood vessels. So it's a very important process of cancer growth. And of course, this is just the one side of the story. The flip side of the story is we're actually doing that. We're using the same technology to monitor drug that targets angiogenesis. So we can use this as a therapeutic technology, use the anti-angiogenic drug to treat angiogenesis, and we can monitor the efficacy of the drug. This is another example. We can see essentially every single blood vessel in the skin, including the smallest capillaries. You can see here, these are capillary beds. The lines are single capillaries. The dots are actually single red blood cells. So we're looking at single cell level already using this technology without injecting any contrast agents. This is all what we call endogenous contrast. We can also detect the color, because oxy and deoxyhemoglobin molecules have different colors, right? So we can quantify the concentrations of both forms, from which we can compute the oxygen saturation of hemoglobin, right? This is a very important parameter, and we can detect arteries and veins by looking at the colors. And this is actually coming out of our finger cuticle, so we can image human capillary loops and watch the color of the blood vessels, and that tells you where the oxygen is released the most. It turned out that the tip of the capillary loop seems to release most of the oxygen, right? So this is very interesting physiology, and one day we can potentially use this to monitor some of the diseases involved in the human capillary level, even some of the diabetic applications. We're trying to push this photoacoustic oximetry to the ultimate level, right? This is the device working at 1 hertz just for demonstration purposes. This is 20 hertz. And we actually work at 200 hertz. At this rate, we can see single red blood cells traveling, right? So you can resolve single red blood cells in real time in vivo and watch how red blood cells bifurcate at this junction, right? We can also look at the color of each red blood cell and look at how oxygen is released from red blood cells. As we know, red blood cells are oxygen carriers. So this is the ultimate level oximetry that allows us to study some of the fundamental biology related to oxygen delivery. And of course, this is very much relevant to cancer metabolism. Now, this is very recent. The data is unpublished. As we know, cancer, primary tumor will not normally kill patients. It's the metastasis that kills the patients. So when the primary tumor somehow transported to a distant site that grows a new tumor, and it grow everywhere, that kills the patient. So CTC, or circulating tumor cells, are very important because this is one mechanism where cancer cells spread. Now we're able to monitor, you'll see these flashes of white dots. These are circulating tumor cells. If we can identify them in the bloodstream, right? You can do multiple things to stop the metastasis, right? You can imagine that potentially you can simply zap this circulating tumor cells using a higher energy laser pulse. That would be one approach. There are certain other pharmaceutical approaches you can think of. I talked about histology, right? So how can we make standard histology non-invasive in vivo? And we can actually detect cell nuclei directly by using photoacoustic microscopy. We get an image that looks almost like standard HE staining histology. So this is the standard histology. This is the same piece of tissue that we acquired using our native contrast. We use the optical contrast. So we can potentially move this into the OR and find out brain tumor margin, for example, right? So that can potentially improve patient survival. We also try to beat that wavelength limit for resolution. So you can see here, this is the standard microscopy at a very fine resolution already. but we improved that further to a resolution of 90 nanometers. So this is sometimes called super resolution imaging. We break through this wavelength over 2 limit for resolution. Now we're detecting mitochondria, and we can see some of the internal structures of a single mitochondrion. So now we're talking about this regime of resolution. So far I've demonstrated the scalability of photoacoustic tomography has applications in animals, cells, all the way to humans. But we're also working on time reversal because eventually we want to beat the penetration limit of photoacoustic tomography, go even beyond what's available right now. So time reversal is possibly one solution. This is a very, very interesting concept. We are actually inspired by astronomy. The astronomers started something very similar because they want to observe the stars clearly. But our atmosphere is going to distort the wave coming onto the Earth. So that actually blurs the images. What they do is they fire a laser beam to generate some sparks. The sparks in the sky will serve as a guide star, as an artificial guide star. And it allows us to correct the wavefront distortion. As a result, you can form a sharp image like this. So it's a very striking difference. All right. Can we do the same thing in biological tissue? Right. So first of all, we don't have a guide star. How do we solve that problem in biological tissue? Well, let me illustrate the time reversal concept using this cartoon. Right. Let's say we have a tiger. There's a bottle of liquid, right? That's going to cause wavefront distortion. So if you have plain wavefront, very nice wavefront on this side, as it propagates through this bottle, it becomes this wavy wavefront, right? This wavy wavefront, if it's reflected by this standard mirror, like the mirror you use every morning, it's going to basically return its wavefront. It'll stay wavy. And when you go through this bottle again, it'll become even more wavy, all right? So the conventional mirror is not going to give you anything that's reasonable. It's not going to give you a sharp image. In fact, by going through the bottle twice, you get twice distorted. Right? You get an image that looks like a distorted tiger. But if you use this special mirror, something called the phase conjugating mirror, that's going to return the wavefront in the same direction. Right? So you notice here, these wavefront curvatures are complementary to the wavefront here. Right? But this phase conjugate mirror is going to return the wavefront in the same direction. This is almost like a time reversal, right? The concept is like a time reversal. You record some scene, right? If the person walks forward, you play it backward, the person is going to walk backward. So we want the optical waves to walk backwards, right? So that's what the phase conjugate mirror does, right? When you go through the bottle, the wavefront distortion is going to be canceled through this bottle. You get a very nice wavefront. Now you can see a very sharp image. So that's the power of time reversal. How do we implement the same concept in biological tissue? We need a guide star, first of all, to begin with, which is really hard to do in tissue. In the early days, our field actually embedded some molecules into tissue that provides a guide star. The trouble is that's invasive. You have to poke the tissue to inject some dye or fluorophores. And it's also not very flexible because once you have that molecule in the location, that's fixed. You can only focus light to that position. So what we do here is to focus ultrasound to a given point. And that ultrasound is going to tag light passing through. Outside the tissue, we detect the tagged photons and time reverse the tagged photons back. And they will come back to the ultrasound focal point. So this technology is called time-reversed ultrasound-encoded or true optical focusing. Another technology is to use photoacoustics as a guide star, right? So this is called optical speckle, right? If you have a camera embedded in a piece of tissue, this is what you will see in general. You got bright spots everywhere. there are actually a lot of photons down there, even when it's deep, but they're all spread all over the place. So using this optical focus, we can actually collect a lot of the bright spots and concentrate them onto this ultrasound focal spot. If we were to use a nonlinear higher order effect, we can actually coalesce all of them into a single spot. So this can be extremely powerful, right? So you enhance the signal by 6,000 times. It's a huge enhancement. Yeah. One more possibility of finding a guide star is to use motion, right? So when there's blood flow, for example, the blood flow can be used to serve as a guide star. Let's see what this move. Oh, now it's moving. So we have this cartoon. If you have a plane behind a cloud, for example, can we actually track that plane, right? So using the motion of the object as a guide star itself. All right. Let me spend a couple more slides talking about one last technology we're working on. In fact, this paper appeared today at noon. Actually, our work made cover of the Nature. As we know, this is the best scientific journal. So we developed a technology that allows us to literally detect the fastest phenomenon possible, right, allowed by physics. As we know, Einstein's relativity theory says nothing can travel beyond the speed of light. So we're detecting the light pulse itself. And the light pulses are traveling in space at the speed of light. We're capturing the light pulses as the light propagates in space, get reflected by this mirror. And if the light ray bends as it crosses the interface of two media, you can see the angles will change, right? Or if I have two pulses in two media, and we can watch them race and see which one will travel faster. And here, and what you saw, a green pulse traveling here, it'll excite some fluorescence, and this red spot is actually the fluorescent light. So we're watching this fluorescent light to decay. And with a single laser shot, we observe this phenomenon. Right? Even the fluorescent decay is on the nanosecond scale because we have picosecond resolution, so that nanosecond looks like eternity for us. So this can be used for very high speed microscopy, or you can potentially use this in combination with the Hubble telescope, for example, to look at very large phenomenon, right, like supernova, for example. So this has very broad applications potentially. And this is the technology we just developed. I don't know how much detail we need to get into this. Maybe I should skip at this late hour. You can ask me questions later if you're curious about this. So I've covered a lot of different technologies here. Started with the motivation and challenges in our field. I talked about photoacoustic CT and photoacoustic microscopy in two forms, time reversal, and what we call CUP, compressed ultrafast photography. Washington University requires me to disclose my financial interest with two companies which have commercialized photoacoustic tomography, and we're funded by NIH through various projects. Thank you very much. I'll be happy to entertain any questions. If there's any. Oh, it's hard for me to see. I'll start from there. Yeah, please.
How can we use this in perhaps other subjects such as engineering, for example?
Use which one?
Photoacoustics.
Use it for engineering.
Engineering or any other part of the medical field, for example.
So you're talking about applications? Potential applications. So tissue So tissue imaging is the main goal for our research, but you can potentially use it for some other applications, even non-biomedical, right? You can imagine robotic vision for underwater, right? So if there's turbidity, what we call when there's in muddy water, for example, right? You can't really see very far underwater. So using photoacoustics, you can overcome the turbidity. You fire some light pulses. If your goal is to see a couple meters beyond you, right? So potentially light can propagate that far, generate acoustic waves, then you can pick that up in a firmer image. Does that answer your question?
Yeah.
Okay. And there was, yeah, back there, please. So it's actually a light-induced sound. So what happens is light is first absorbed. So you generate a transient heating, a very short temperature rise, right? So on the order of nanosecond scale, because we use nanosecond laser pulses. And so that temperature rise, as you can imagine, is going to cause thermoelastic expansion. And that pushes tissue. Even though this is very minute, but every millidegree gives you 8 millibars or 800 pascals of pressure rise, which is already detectable. So if you generate hundreds of milledegrees temperature rise, then you get a very bright signal to detect. And that allows us to form an image. So this is called the photoacoustic effect. So basically it's a photothermal and thermal acoustic. And in the end, we just call that photoacoustic effect. The standard detectors has to be coupled acoustically to the tissue. You can directly touch it, just like when you perform ultrasound imaging in the hospital. They typically apply some gel on the skin to ensure acoustic coupling. Water coupling is one way. Gel coupling is more convenient for a lot of applications. However, our field is also developing non-contact sensing of acoustic waves through optical interferometry. So if you shine light onto the tissue surface, if there's vibration on the surface, that displacement can be picked up through optical interferometry. And that can be translated into acoustic wave as well. So that's a potential non-contact version. But for now, most of the implementations are based on the contact version. It's more traditional and it's better developed. Yeah, please. Mm-hmm. So right now, for breast cancer imaging, X-ray mammography is still the gold standard. So we're still sticking with that one. There are two types of directions that our field is taken. One is to supplement X-ray mammography, because X-ray mammography, as sensitive as it is, they have trouble with young women with radiographically dense breast. So where they really feel miserably. The other flaw with X-ray mammography is the very high false positive rate. So that causes a lot of, biopsies, subsequent tests, which turned out to be unnecessary eventually. So can we use photoacoustics to supplement, right? If X-ray detects this as positive, can we confirm if this is truly positive or not by detecting the functional information? Another way that's more, takes longer, it's going to take longer to validate, is to start from breast cancer screening to begin with. So can we use photoacoustic tomography to screen for breast cancer without using ionizing radiation at all? Just start from the functional contrast provided by photoacoustics. The reason I said it's going to take longer is because even though breast cancer is a huge problem, the rate of incidence is still relatively low. You know, you have to test like 1,000 patients to get enough patients with breast cancer so you can establish the statistics. So it's a more difficult problem. Any more questions? Yeah, please. Oh, the images, right? Yeah, so it's a very good question. You're still talking about photoacoustic tomography, right? So there are two different ways of getting an image. With the microscopy technique, with a single laser shot, you get a 1D image, which is depth resolved. So you illuminate along the vertical axis, for example. Then you generate essentially a volumetric acoustic source, but then we use ultrasound transducer to pick up the signals. So the acoustic time of arrival is going to tell you the depth information. You get a 1D image with a single laser shot. Then you have to scan linearly to get a 2D image. Then you have to, if you want to get a 3D image, then you have to raster scan. That's one way of getting an image, 3D image. Another way is to use an array of transducers. So for example, like the ring array I showed, right? So we basically put a ring of 512 elements surrounding the head of animal or the body of animal or wherever we want to image, like the breast. Then we use a broad field light illumination. We don't focus light here at all. We just let light photons basically bathe the tissue. You generate a 3D volumetric source. Then your ring is going to detect signals from a slice because we acoustically focus in the elevational direction, the height direction. And then we detect signal from this slice. Then we use image reconstruction to form a 2D image. And if you want to get a third dimension, of course, you do Z-scan. Now, this is with a 1D array. Now, if budget is not a problem, then we can potentially get a 2D array. I mean, in the ideal world, you can imagine we can surround the breast or the head with a lot of transducers. In that case, with a single laser shot, you should be able to get a 3D image. But right now, the technology allows us to get a ring array or 1D array at a reasonable price. But a two-dimensional array is right now quite expensive. In fact, the ultrasound world has been working on that for quite some time. And they're talking about 1.5D. In other words, one-dimensional density is high, the second dimensional density is much lower. Because you simply cannot have that many transducers, ultrasound transducers, and still maintain the cost. Yeah, please, Rose. Mm-hmm. So I was trained in laser physics. So I got my Ph.D. from Rice, and my Ph.D. thesis was actually on a chemistry project. After I got my Ph.D., I decided to switch to something more applied. So I worked for MD Anderson Cancer Center. There was a laser lab. I think that was a very good fit for my career goal. So for applications in the OR, I think there are several potential applications. One of them is the cancer demarcation, as I mentioned. Can we have a complete removal of tumor? So you minimize the recurrence rate. Another application, as I mentioned, is brain oxygen consumption monitoring. We want to do that non-invasively. So this is what's so good about WashU, right? So even though most of my lab space is in the Hilltop or Danforth campus, I have a lab in the medical school as well. We have a lot of collaborators, so physicians, WashU physicians are very eager to work with engineers. They want to work with us. they knock on my door or come to my office, want to work with engineers to apply our technology to their problems. So we're targeting multiple problems, right? GI tract, breast, breast cancer staging, melanoma, you name it. So we want to see the real impact in the human side. The photoacoustic tomography has been commercialized by several companies now. I personally work with 2 of them. So for preclinical imaging, it has been established. So there are products available, they're being sold. But for human imaging, it's not there yet. So I was not allowed to mention the name of the company which has licensed our IP for human imaging. So we're very happy that this is moving forward. So it's going to take some time. Eventually, I'd like to see this as a daily used tool by physicians. Any more questions? Well, thank you all very much again.